Structure. Important terms. Electron, it was discovered by J.J. Thomson. It is negatively charged particle. Electron is a component particle of a cathode rays. Cathode rays Cathode rays were discovered by William Crookes and J.J. Thomson. Cathode ray travel in straight line. Cathode ray consists of negatively charged particle known as electron. Proton. Proton was discovered by Goldstein and it is positively charged particle. It is a component particle of anode rays. Anode rays. Anode rays travel in straight line. They are positively charged. The Le upon m ratio of these rays is similar than that of electron. Neutron. Neutron was discovered by James Chadwick in the following nuclear reaction. Atomic mass 9, beryllium atomic number 4 plus helium atomic mass 4, atomic number 2 gives product as carbon atomic mass 12, atomic number 6 and neutron with atomic mass 1, atomic number 0. A neutron does not carry any charge. Atomic number, the number of proton present in the nucleus of the atom, is called atomic number Z. Atomic number is equal to number of positive charge on nucleus equal to number of proton in nucleus. Number of proton in nucleus equal to number of electron in neutral atom. Mass number, it is the number of nucleons or the number of protons and neutrons in the nucleus of an atom A. Mass number is A equal to number of proton or atomic number Z plus number of neutron or number of neutron is equal to A minus Z. Electromagnetic radiation. This consists of electric and magnetic field that oscillates in direction perpendicular to each other and perpendicular to the direction in which the wave is traveling. They do not need any medium for propagation. For example, X-ray, gamma rays. All electromagnetic radiation travel with the velocity of light. Wavelength, it is the distance between two nearest crest or nearest trough. Unit is m or centimeter or nanometer or Armstrong is 1 meter is equal to 10 raised to square, centimeter equal to 10 raised to minus 9, 10 raised to 9, nanometer equal to 10 raised to 10 Armstrong. Frequency, it is the number of wave which pass through a point in 1 second. Unit is equal to hertz or cycle per second. C equal to mu lambda. Velocity, it is the distance covered in 1 second by the wave. Wave number, it is reciprocal of wavelength or the number of wavelength per centimeter. Planck's quantum theory. Radiant energy is not emitted continuously but discontinuously in the form of packets and quanta. Energy associated with each quantum is directly proportional to frequency of the radiation. E is directly proportional to V or equal to hV, where h is Planck constant. H is equal to 6.624 10 raised to minus 34 joule second. Energy associated with all the quanta is given by E is equal to NH V, where N is the number of quanta. A quantum in case of light is called photon. Thomson model of atom. The positively charge of the atom is like a sphere in which negatively charged electrons are embedded. It is also known as plum pudding model. Rutherford alpha scattering experiment. A beam of alpha particle was made incident on thin foil of gold, 0.0004 centimeter thick, and across the foil, a screen of zinc sulfide was kept. Rutherford model of atom. An atom consists of a positively charged heavy part called nucleus, where most of the mass of the atom is concentrated. Proton and neutron present in the nucleus. Size of the nucleus is very small compared to the size of the atom. Around the nucleus there is an extranuclear part in which there are electrons. Electrons revolve around the nucleus in circular orbits like planets around the sun, and they are called planetary electrons. Failure of Rutherford's model. An electron, being a charged particle under accelerations around the nucleus, should lose energy continuously. It should move closer and closer to the nucleus due to loss of energy, and ultimately should spiral down into the nucleus. So the atom should collapse, but atom by itself is stable. Bohr model of atom. An atom has a nucleus which is positively charged and very small. It contains protons and neutrons. Negatively charged electrons are moving around the nucleus in a circular orbits. An electron cannot just revolve anywhere, but it can only revolve around the nucleus in certain permitted orbits, where angular momentum of the electron is equal to nh upon 2 pi, or mvr equal to nh upon 2 pi, where n is equal to 1, 2, 3, r is equal to radius of the orbit, and h is Planck constant. In each stationary orbit, the electron has a definite quantity of energy in its own stationary orbits. The electron is said to be in the ground state. An electron in the ground state can absorb a certain amount of energy and can shift it to a higher energy state called excited state. In the excited state, electron is unstable and jump back to the ground state with the emission of energy. The energy absorbed or emitted during the transition is equal to the difference in energy of the two orbits. Rule of the orbit. R is directly proportional to n square upon z. Velocity of the electron v is directly proportional to z upon n. R1 upon R2 is equal to n1 square upon n2 square multiplied by z2 upon z1. Velocity of the electron v1 upon v2 is equal to z1 upon z2 multiplied by n2 upon n1. Radius of the orbit r is equal to 0.529 multiplied by n square upon z Armstrong. Velocity of the electron v is equal to 2.188 10 to 8 multiplied by z upon n centimeter per second. Energy of the electron in different units. Energy of the electron En is equal to minus 2 pi m e square z square upon n square h square. En is directly proportional to minus z square upon n square. E1 upon E2 is equal to z1 square z2 square multiplied by n2 square upon n1 square. Energy of the electron different units. Minus 13.6 z square upon n square. Electron volt per atom. Minus 1312 z square per n square kilojoule per mole. Minus 21.79 10 to minus 19 z square per n square joule per atom. Minus 313.6 z square per n square is kilocal per mole. Different modes of transition between two orbits. Different modes of transition between two orbits. N1, N2, N3. Delta E1 is equal to E2 plus E3. So V1 equal to V2 plus V3, and 1 upon lambda 1 equal to 1 upon lambda 2 plus 1 upon lambda 3. Total number of spectral lines for a transition number of line epsilon in the bracket n square minus n1. For example, if transition is from 6th orbit to 2nd orbit, number of line is equal to epsilon 6 minus 2 is equal to epsilon 4 q's. 4 plus 3 plus 2 plus 1 equal to 10. Rate constant V bar is equal to 1 upon lambda is equal to R. in bracket 1 upon n1 square minus 1 upon n2 square bracket z square, where n2 is greater than n1 are the number of orbits. Z is the atomic number, R is the Rydberg constant, is equal to 109678 per centimeter. Hydrogen spectrum. Name of the series spectral region N1, N2. Lyman series spectral region ultraviolet N1 is 1, N2 is 2, 3, 4, 5. Balmer series is a visible spectral region N1 is 2, N2 is 3, 4, 5, 6. Paschen series under the infrared spectral region N1 is 3, N2 is 4, 5, 6, 7. Bracket series under infrared spectral region N1 is 4, N2 is 5, 6, 7, 8. Pfn series under the spectral region infrared N1 is 5, N2 is 6, 7, 8, 9. Humphrey series under the infrared spectral region N1 is 6, N2 is 7, 8, 9, 10. Spectral series. Line of maximum wavelength, line of minimum frequency, line of minimum wavelength, line of maximum frequency general. N2 is equal to N1 plus 1, N2 is infinity. Lyman series is N1 equal to 1, N2 is equal to 2, N1 equal to 1, N2 equal to infinity. Balmer is N1 equal to 2, N2 is equal to 3, N1 is equal to 2, N2 is equal to infinity. Paschen series N1 is equal to 3, N2 is equal to 4, N1 is equal to 3, N2 is infinity. Bracket series N1 is equal to 4, N2 is equal to 5, N1 is equal to 4 and N2 is equal to infinity. Pfn series N1 is equal to 5, N2 is equal to 6, N1 is equal to 5, N2 is equal to infinity. Humphrey series is N1 is equal to 6, N2 is equal to 7, N1 is equal to 6, N2 is equal to infinity. Drawback of Bohr's model. It is only applicable to single electron species H, He+, Li 2+, Be 3+. It does not explain Stark effect or Zeeman effect. It has no explanation for fine spectrum. It is not in accordance with the Broglie dual nature of matter and Heisenberg uncertainty principle. The Broglie dual nature of matter. All moving objects have a particle as well as a wave character. The wavelength associated with the moving particle is called de Broglie wavelength lambda. This principle is significant for microscopic particles like subatomic particles and does not have any significance in daily life. Lambda is equal to h upon p or lambda is equal to h upon mv. Heisenberg's uncertainty principle. It is impossible to measure simultaneously both the position and momentum of a particle with absolute accuracy. Delta p delta x is greater than or equal to h upon 4 pi, where delta p is the uncertainty in momentum, delta x is uncertainty in position, and h is Planck constant. Wave mechanism, model of atoms. The classical mechanics could not describe the behavior of electrons correctly. Therefore, a model was proposed which could incorporate uncertainty principle and dual natures of matter. This approach was called quantum mechanics or wave mechanics. It was developed independently by Heisenberg and Schrödinger. Schrödinger wave equation. Schrödinger described the behavior of the electron in the form of mathematical equations called Schrödinger wave functions. Lambda square wave function upon lambda x square plus lambda square wave function upon lambda y square plus lambda square wave function upon lambda z square plus 8 pi square m upon h. In bracket E minus V wave function equal to 0. E is the total energy of the electron. V is the potential energy of the electron. The only dependent variable in Schrödinger wave equation is wave application, wave amplitude or wave functions. Lambda wave function depend upon coordinates of the particles. So in case of electrons, wave function square is taken to the probability of finding the electron at a given point at a given instant of time. Quantum number. There are set of 4 numbers assigned to describe an electron in an atom. Principal quantum number n. It gives the number of shell to which the electron belongs. Its value can be 1, 2, 3. Larger the value of n, greater is the distance from the nucleus and energy of the electron. Maximum number of electrons in a shell can be 2n squared. Azimuthal quantum number L, also called angular quantum number or subsidiary quantum number. For every value of n, L can be 0, gives n minus 1. Value of L corresponds to the subshell or sublevel of energy within a shell. Order of energy distance from the nucleus. F is greater than D, D is greater than P, P is greater than S. Orbital angular momentum of the electron mu is equal to h bar square root L in bracket L plus 1 equal to h upon 2 pi square root L in bracket L plus 1. Magnetic quantum number m. It gives the number of preferred orientation of electron in the pressure of magnetic field which are co-orbital. For every value of L, m can be formed minus L gives plus L through 0. Total value of m for every value of L is 2L plus 1. S is 0, 0, first orientation. P 1, minus 1, 0 plus 1, 3 orientation. D is equal to 2 minus 2 minus 1, 0 plus 1 plus 2 gives 5 orientation. F is equal to 3 minus 3 minus 2 minus 1, 0 plus 1 plus 2, 7 orientation. Orbital of the same subshells have same energy and are known as degenerate orbital. Spin quantum number S. An electron revolves around the nucleus and also spins about its own axis. Spin produces angular momentum in a particular direction. S is equal to plus 1 by 2 for clockwise spin and minus half for anti-clockwise spin. Rules for the filling of the electron in orbital of an atom. Pauli's exclusion principle. No two electrons in an atom can have same set of 4 quantum number. An orbital can have a maximum of the electron with the opposite spin. Aufbau principle. Aufbau is a German word that means building up. Filling of electron in various subshells of an atom takes place in the increasing order of the energy, starting with the lowermost, that is 1s, 2s, 2p, 3s, 3p, 4s, 3d and 4p. Bohr's-Bury rule, n plus L rule. The subshell with lower value of n plus L is filled first. For example, 4 is filled before 3d because of the following rule. 4s, n is equal to 4, L is equal to 0, n plus 1 is 4. 3d is n is equal to 3, L is equal to 2, and plus 1 will give 5 for the 3d orbitals. Hund's rules of maximum multiplicity. This rule is used for filling of electron in degenerate orbitals. During filling of electrons in degenerate orbital of a subshell, pairing does not take place till each orbital get one electron with parallel spin. Atomic number 21 names scandium. Electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Atomic number 24 chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Atomic number 25 is named manganese. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. 26 iron. Atomic number is 26. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 36. Atomic number 28 is nickel. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 38. Atomic number 29 copper. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 30, 3d10. And copper Z is 29. Atomic number is 29. So 4s1, 3d10 is there because the 10 is more stable field configuration. And chromium Z 24, 4s1, 3d5 is there because d5 is more stable half field configuration. Electronic configuration of iron. In nickel, 2 plus electrons are first lost from 4s and then from 3d. For nickel, Z is equal to 20 for neutral atoms. Argon 4s2, 3s8. For nickel 2 plus argon 4s0, 3d8. There are 2 unpaired electrons, so it is paramagnetic. Spin magnetic moment is equal to square root n in bracket n plus 2 bm, where n is the number of unpaired electrons. Shapes and orbitals. S orbitals gives L equal to 0, M0 only one orientation spherically symmetrical. P orbitals give L equal to 1, M is equal to -1, 0 plus 1. This 3 orientation double shaped. D orbitals give L is equal to 2, 5 orientation. Orbital dz square 0 shape donuts set e.g. orientation along the axis. Dx square y square plus minus 2 double dumbbell e.g. along the axis. Dx square plus minus 2 double dumbbell 2g set between the axis. Dy square plus minus 1 double dumbbell t2g between the axis. Dzx plus minus double dumbbell t2g between the axis.